Hey there, physics fans. Today we're going to work text problem 5-62. So the first step is that read step. So in this problem, I read some keywords. I read that we're dealing with charges, but specifically we're dealing with a positive Q1, and then two negative charges, Q2 and Q3. And they're all placed in this corners of the configuration of this triangle. And we want to know what is the force on Q1. So that leads us to our task. Let's calculate the sum of the external forces on Q1, on that charge 1. So we go into our physics, and we are dealing with charged particles. So we're definitely going to think electrostatics and magnetism, but there's nothing in this problem that indicates a magnetic field or anything. So we know we're focusing only on this electrostatics piece, which means that the force we're dealing with these charged particles at this time is the electrostatic force. So that is the equation. It's under your Newton's second law portion of your PRC, where the electrostatic force, which is a vector, the magnitude of it is going to equal Coulomb constant, that's K, that's a value you can find on the back of your PRC, times the magnitude of charge 1 times the magnitude of the second charged particle, all that over that R, the distance between the two charged particles. Okay, and that distance is squared. So in our givens, we have Q1, we know Q2, Q3, we have, we need to also know the distance between Q1 and Q2. And we also need to know the distance between Q1 and Q3. Okay, so we have all of those distances, which is pretty nice. We're given all of those values. So we can label it right over here, or this distance right here, that's the distance between Q1 and Q3, and 5 meters is the distance between Q1 and Q2. Okay. So now we can go into our assumptions. And we're going to say that 1, it's isolated, meaning that there's no other charged particles within the vicinity of these 3. And then we're also going to say that the mass is so small we don't have to consider the effects of gravity. To consider the effects of the gravitational force or any other forces. So we can put that there. All right, so now we're ready for that solve step. Okay, so first step, whenever we're dealing with forces, we pretty much always, every time, yep, we definitely do. We got to do that free body diagram all over again. All right, so we're going to do our free body diagram. And this time, though, it's for Q1, okay? Because this is we want to know that all the sum of all external forces acting on Q1, not the other charged particles. That's particularly the one we care about right now. So, of course, we start with isolating the body. I'm going to draw a nice little circle. And then the second step is always label those external forces. So in this case, you notice Q1 is positive and Q3 is negative. So that means Q1 wants to go, it is attracted to Q3. So there's the electrostatic force acting on coming from Q3, being acting on charge 1. So we can write it right that. And then we have another force. In this case, we've got an electrostatic force coming from charge 2 that's acting on charge 1. So I can draw then, again, Q2, charge 2 is negative, and charge 1 is positive. So there's an electrostatic force that is acting coming from charge 2, acting on charge 1. I'll draw a nice little sketch there. All right, so, and one thing I am forgetting to to make it clear for myself later, I'm adding the subscript of E. Because later on in this block, we're going to add 2 more forces. We're going to add 2 different types of magnetic forces. And it's always important to get accustomed to the fact that F sub E means electrostatic force, and F sub B is going to mean magnetic force. All right, so now we're ready for that third step of the free body diagram process, which is to draw a coordinate axis. I'm just going to draw that right here. And nothing's rotating, so I'm not going to draw a direction of positive rotation. But now I'm ready to draw the critical angles and critical dimensions. Again, nothing's rotating, so I don't need to be concerned with drawing a critical dimension, but I do have a critical angle where, if you notice, the electrostatic force coming from charge 2 is not only in the y or only in the x. It is at some angle away. So we can solve for that theta later on. We can actually solve for it right now. So I'm going to go over here. We are given, I'm going to highlight this in green, we're given a hypotenuse, we're given a length, and we're given another length. So we have all the details using those distances to calculate what theta is. So I'm going to use my SOHCAHTOA. And I like using TOA the best. So I'm going to do tangent of theta is equal to opposite over adjacent, which is equal to 4.0 meters divided by 3.0 meters. So my theta is going to be that tangent of 4.0 divided by arctan, 4.0 divided by 3.0, and that gives me an angle of 53.13 degrees. And I'm not rounding to sig figs yet, because I want to make sure I don't round my sig figs until the very end. So I'm going to leave it as 4 sig figs. All right, so now we're ready to actually do the rest of Newton's, applying this external forces. So when we say the sum of all external forces, that's going to be adding up this electrostatic force coming from charge 2 acting on charge 1, plus we're going to have to add up the electrostatic force coming from charge 3 acting on charge 1. We got to add those two up together. Well, these are vectors, so I got to resolve it out into my x and y. So I'm going to have the sum of all external forces in the x direction. That's going to equal my electrostatic force from charge 2 acting on charge 1 in the x direction, plus my electrostatic force coming from charge 3 acting on charge 1 in the x direction. Well, first up, the electrostatic force coming from charge 3 acting on charge 1, there is no x component, so that goes straight to 0. So that means I'm left with only the electrostatic force coming from charge 2 acting on charge 1. And so I can resolve that out by now applying my equation for electrostatic force. So Coulomb's constant times the magnitude of charge 2 times the magnitude of charge 1. All that's divided by this distance r1, 2, so the distance between the two squared. And then we're good to go there. Then we need to multiply, because this is the magnitude of the force. It's only the x component, so it's the magnitude times sine of theta, the angle we solved for, because we're looking for, and I'll highlight it, we're looking for this portion right here of that electrostatic force, which is why I used my SOHCAHTOA. The sign is the opposite over adjacent. All right, so it's the magnitude of the entire electrostatic force coming from charge 2 acting on charge 1 multiplied by sine of that angle between them. So I substitute everything in, and that's going to give me a value of 2.3 times 10 to the negative 5th newtons. And that is the x component of my electrostatic force. Some of my forces in the x direction, the electrostatic forces in the x direction acting on charge 1. So now I can do the same thing over in the y direction. So I do the sum of all external forces in the y direction is equal to, and this is where I'm going to add up again, my electrostatic forces coming from charge 2 acting on charge 1 in the y direction plus my electrostatic forces and charge coming from charge 3 acting on charge 1 in the y direction. So now I can add those up. Well, here's the interesting thing. For both of these forces, they actually are coming, if you look, they're coming in the negative y direction. So I'll highlight that part right here. Right? So positive y points up. These forces are pointing in the negative y direction. So they're going to be negative values. So I have a negative Coulomb's constant times charge 2 times charge 1, all that divided by that distance squared. Then I also have a minus, excuse me, I almost forgot my, I gotta make sure I identify my x component there, my y component. Make sure I'm adding this cosine of theta because that electrostatic force coming from charge 2 acting on charge 1, it has a y component. So I have to use my cosine according to SOHCAHTOA. And then I'm going to subtract the electrostatic force coming from charge 3 acting on charge 1. And that is just Coulomb's constant, the magnitude of Coulomb's constant, times Q3 times Q1, or charge 3 times charge 1, all that divided by the distance between the two squared. So I have that listed. And now I can plug it all into my calculator, all of those values there, and I get that the sum of the forces acting in the y direction is equal to negative 3.7 times 10 to the negative 5th newtons. Okay, so now I have an x component and a y component of my force, the sum of all the forces acting on charge 1. So that's what I'm going to write here, is that the sum of all the external forces on charge 1 is equal to 2.3 times 10 to the negative 5th I hat minus 3.7 times 10 to the negative 5th j hat. And that's going to be all in newtons. And that's our answer. Sweet. So that leaves us left with just the check step. Well, we are units of newtons, so that's good. Sig figs, problem definitely has this listed as 2 sig figs. And then reasonable. And it is reasonable. The reason why we know it's reasonable is because charge 1, it goes back to charge 1 is a positive charge. So it is going to be attracted to both charge 3, and it is going to be attracted to charge 2, which means if our coordinate axis is that x and positive y going up, then it's going to want to go and travel in the negative y direction, and it's going to be some mixture between both charge 3 and charge 2, so it will have a positive x direction motion. So that's where it makes sense with what we have listed here in our values. All right, physics fans, that completes text problem 5-62. Good luck, and make sure you definitely go in to speak to your instructors, ask questions, of course, and crush this. You got this.